All right, flipped chemistry, how you doing? We are here to talk about art. Geometry. Chemistry. Hey, let's talk about all three. We're talking about molecular geometry today, how molecules are arranged in three-dimensional space. And this is going to take something that we've talked about starting back with Lewis dot structures and going on to talking about different kinds of bonds. Now we're going to put it all together and make these things into shapes. So it's actually a really cool concept, and it's one of my favorite things in chemistry. So I hope you enjoy it too. Let's get started. We're talking about the Vesper Theory, and this is going to be the underlying idea that controls how bonds work and how molecules are arranged into the shapes that they are. So Vesper stands for valence shell electron pair repulsion. Basically what that means is electrons are negative things. And so if I'm an electron and there's another electron over there, I'm negative, it's negative, we want to be as far away from each other as we can be. And so electrons repel each other. Now they're attracted to the nucleus, but they're repelled against each other. So they try to be as far away from each other as they can be. And that controls the geometry of bonds, because if you've got a pair of electrons hanging out on this side and another pair of electrons hanging out over here, they're going to orient themselves to be as far away from each other as they can be. And so the number of bonds coming out of an atom will arrange themselves so that there's maximum distance in three-dimensional space. So that controls how these bonds are arranged. Bonds are created at angles which maximize the distances between the valence electrons of an atom and those atoms bonded to it. Okay, so here we go. It's all about running away. It's all about electrons getting as far away from each other as possible. As we're looking at this, we need to consider how many regions of electronegativity an atom has in its valence energy shell. So remember that almost every atom wants to have 8 electrons in its outermost shell. And remember also that electrons come in pairs, that there's 2 electrons per orbital. I'm sorry, yes, per suborbital. And so there are in 8 electrons 4 pairs. And so most atoms will have 4 regions of electronegativity, whether they're bonds or whether they're unshared electrons. And so given any one atom, there will almost always be 4 regions of electronegativity. Here's an example of this. Here's atom A, and it's bound to 4 other things. And so we call them all B. They don't have to be the same thing, but you get the idea. One atom bound to 4 other things. And there are 4 regions of electronegativity. Now, to get 4 things as far apart from each other as possible, it arranges it into what's called a tetrahedron. And you're familiar with this concept from geometry as well. And it winds up looking like a jack, where no matter how you throw a jack, 3 of its feet land on the ground and 1 is sticking straight up. And that's the same shape here. And if you measure the angle, the bond angle, from any one leg of that tetrahedron to another, it's 109.5 degrees. And then however else you would try to arrange those things, they'd be closer than 109.5 degrees. And so this tetrahedron is the stable arrangement for something with 4 regions of electronegativity. There could be 4 bonds, it could be 3 bonds and a pair of electrons, it could be 2 bonds and 2 pairs of electrons, but as you go through this thing, you're going to almost always find 4 regions of electronegativity. So let's look at some pictures. This is methane, a carbon and 4 hydrogens, okay? And it's tetrahedral, 109.5 degrees between all of these angles. If you measured here to here, here to here, here to here, no matter which 2 you pick up and measure, it's 109.5 degrees, okay? And so it's kind of like the center of a triagonal pyramid. There you go. I don't know why I couldn't say that. So that's if you'd started in the middle and drawn to the 4 corners of that, right? That's a tetrahedron. And so this is another way of looking at that. This is the ball and stick model. Now, sometimes these bond angles don't represent a bond. Sometimes it's a pair of electrons hanging out in that 4th position or 2 of the 4 positions. And so we have other names for the shapes that are created when our tetrahedron doesn't have 4 bonds, but it's still the same bond angle, more or less, right? We have a pyramid, and the tetrahedral pyramid is still a tetrahedral shape. It's just that one of the bond angles is a pair of electrons, and the other 3 represent some bond to another atom. Or you could have the bent 109, and that has only 2 things that are atoms and 2 things that are pairs of electrons. So if I were to cover this up, right, and then you'd have this bent shape, and then a pair of electrons and a pair of electrons. Or a linear, where only one of them is another bond, and the other 3 positions are all electron pairs, in which case you've just got a straight line. You've got 2 things bound to each other. The only way to connect 2 things is with a straight line. Okay, so here's another example of a tetrahedral pyramid. Okay, and this is another example of a bent shape. Here's oxygen and 2 fluorines, and the oxygen has 2 other things that it's bound to, but they're just electron pairs at this point. And so we have this bent shape. And then here's another one. This is water. Water winds up with this the same shape. It's a tetrahedron, but 2 of them are bonds to hydrogen, and 2 of them are just electron pairs. Now, this is 104.4 degrees. Don't get too stressed out about why it's 104.4, not 109.5. Don't worry about that. It's the same shape. Then linearly, fluorine to fluorine, there's only one way to connect 2 things, so we call that linear, right? And that looks like a Smurf butt, but no, that's supposed to be a diatomic molecule. 2 atoms joined together, sharing a covalent bond, and so they're right next to each other, and their other electrons would be floating around out here somewhere. Or it's a Smurf mooning you, however you want to look at that. Okay. If an atom has 3 regions of electron density, then it's going to be a different shape. The tetrahedral is the most stable way to have 4 things hanging out. If you have 3 things hanging out, then the most stable way is actually to create a plane, which is kind of obvious because any 3 points defines a plane, right? And so we have here atom A bound to 3 other things, 3 other entities. And you put them all in the same plane, and you separate them by 120 degrees. And this is called trigonal planar. Planar because it's in a plane, and trigonal because there's 3 things, right? If only 2 of them go to atoms, then we call it a 120 bent. It looks still like a bent, like water molecule, but it's a bigger gap between them because there's only 1 pair of electrons that are pushing on them. 1 out of 3 would obviously be linear again. Okay, so here's some pictures. This is trigonal planar, and then another trigonal planar, boron hydride. Boron is one of those strange things that's okay with not 8 electrons in its outermost shell. So it's okay with looking at 6 electrons, so it has 3 bonds to hydrogen, and it's in a trigonal planar shape. This is another one. Now, carbon likes to have 4 bonds, but it's sharing 2 of them with oxygen, so there's only 3 regions of electron density around this carbon, so it's also trigonal planar. Okay, this is another model of that same molecule, right? And so again, the oxygen double bonded to the carbon makes only 3 regions of electron density, and it's trigonal planar. You can have bent as well. This bent is different than the water molecule kind of bent. Here you only have 1 other pair of electrons, and so there's 3 regions of electron density. 2 of them go to bonds. 1 of them is just an electron pair, and so you wind up with this where 120 degrees is the angle here, and that's again different than the water molecule version where the answer was 109.5, or in this particular example 104.4. Don't stress about the reason, but 104 versus 120, not the same thing. This is a bent trigonal, this is a bent tetrahedral. Okay, and then of course linear. If there's only 2 regions of electron density, then you have a straight line, and so it's a 180 degree bond angle. And this is almost always because of double or triple bonds. You don't normally get this with things that only have 1 bond. So acetylene is an example of this. Carbon triple bonded to carbon with a single bond, hydrogen on each side. Each carbon only has 2 regions of electron density, right? And so it winds up as a straight line molecule. This is that same model done in a different format, but you can again see 3 bonds and single bonds, and so it's a straight line, 2 regions of electron density. Carbon dioxide is a very familiar example as well. Carbon, 4 bonds, but 2 of them going to each oxygen, so again, you wind up with a straight line, 180 degree bond angle. Beryllium hydride, same thing. Beryllium can be okay with only looking at 4 electrons, so 2 over here, 2 over here, got a straight line. polar influences. Now, we talked about polarity last chapter. We're going to get more into the concept of polarity in this chapter. How do you know if a molecule is polar? Well, you need to know if the individual bonds are polar. But before you even care about that, you just look at the molecule and see if it's symmetrical. Because if the molecule is symmetrical and the same bonds are going in opposite directions, no matter how you turn the thing, then it's non-polar. It may have polar bonds, but all of the partial positive and partial negative parts of that molecule are balancing each other out. And so the molecule as a whole is non-polar. So if a molecule is symmetrical, it's non-polar. If a molecule is asymmetrical, it may be polar, but first you need to look at the bonds and see what the dipole moments of those various bonds are. Okay? Some shorthand that we use is this little arrow, where you draw an arrow from the region of partial positive charge to the region of partial negative charge. You put a little hash mark across there to indicate this is where the thing is positive, right? And then it points to where the electrons are going more. And then you can indicate the strength of this dipole moment with a value called mu. That's the lowercase Greek letter m, okay? And then they'll say mu equals, and that will tell you how polar that bond is. That's not something we're going to get into measuring in high school chemistry, but if you were to take some analytical chemical classes later on in college, you'd get into measuring dipole moments, okay? But this is for right now, we're just going to take their word for it, that the strength of this dipole moment is whatever they tell us that it is, okay? So a dipole moment on a molecule represents over here is more positive, over here it's more negative, and that is called the dipole moment. And the strength is expressed as a value of mu. Okay. Here is some examples. In ammonia, the nitrogen pulls harder on the electrons than the hydrogens do. It wins the tug of war. So even though it is a covalent bond, the electrons spend more time around the nitrogen than they do around the hydrogen. So we represent the dipole moment this way, saying that as you go up on the molecule, you find more electronegativity, and as you go down on the molecule, you find more electropositivity. And the strength of this dipole moment, mu equals 1.46. Compare that to nitrogen trifluoride, where the nitrogen is losing the fight with fluorine. And so the electrons all spend more time away from the nitrogen than they do on the nitrogen. The dipole moment is the opposite direction. But the difference in electronegativity from nitrogen to fluorine is a lot smaller than the difference in electronegativity from nitrogen to hydrogen. So the strength of mu here, the strength of the dipole moment is much larger than it is over here. 0.24 is much smaller. This is a polar molecule, but it's a weakly polar molecule versus ammonia. Okay. Just some other examples. This is carbon double bonded to an oxygen and then a hydrogen on both sides. Okay, so the carbon and oxygen is a polar bond, and the carbon wins the fight over the hydrogen. So the carbon pulls harder on the electrons than the hydrogen does, and then the oxygen pulls harder on the electrons than the carbon does. So as a whole, electrons are going this way, right? So we represent the dipole moment this direction. It's a fairly polar molecule. 2.2 is the value of mu. Now here you have the same carbon-oxygen dipole moments on each bond, but what's interesting is this is symmetrical, right? The two oxygen double bonds are exactly opposite each other. So while the carbon is losing the fight every time, it's losing the fight in this direction and losing the fight in that direction, and so you wind up with a balanced molecule. This has a mu of 0. There are polar bonds, but the molecule as a whole is not polar because it's symmetrical. No symmetrical molecule is polar. Okay, another example, carbon and chlorine, and then 3 hydrogens. Well, the hydrogens lose the tug of war against carbon. Carbon's more electronegative, but chlorine is more electronegative still. So the electrons are over this direction, and then they're over this direction. So the chlorine is the big daddy winner, and this is not a symmetrical molecule, and the electrons all tend to spend more time up here around chlorine than they do around the hydrogen. So the dipole moment is in this direction, and this particular picture didn't label the value for mu, but it would be pretty significant. Okay? If you have any questions, please let me know, and I will answer them as quickly as I can. I'll see you tomorrow in class. God be with you.